as I said, it's just a short form for distinguishing between the clauses. So this is the same definition as this one, where you say propositional letters are formulas if phi is a formula, etc., etc. So if you write it like this instead, it means something like or, right? Phi is a formula if it is P, or if it is not phi, where phi is a formula, or if it is phi and psi, etc. So they don't mean anything else. It's just a short way of writing inductive definitions of formulas. I see there is a WeChat discussion about connections. I'm assuming that you you can do that. You can carry on that discussion by yourselves. Otherwise, we can talk over WeChat after class. So let's see. There was one more question. When will the homework be assigned and handed in? So I think the homework normally, we haven't really decided that yet because I wanted to see how this first class goes. And if everything works as it should. But if it does, normally you would be assigned homework in the middle of the week, or maybe on Thursday, and then it should be done, it should be handed in by Monday. That's my first plan. I have to discuss this with Jialiang, and we'll see. But something like that. You will get more information about the homework soon. Okay, so let me go back to logical consequence. You have the definition on this page, and this is the basic logical notion, I would say, because logic, in a sense, is about consequence. It is about what follows from what. And here we have a precise definition of that in propositional logic. There are some other notions, related notions, and they're on this page. So we say that a sentence is logically true or a tautology, and we write it turnstile phi with nothing to the left. And what does that mean? Well, I think you know what it means. It means that phi is true in every valuation. We say that phi is contradictory if it's not true in any evaluation, is if it's false in every valuation. We don't have a symbol for that, but we don't need one, because to say that phi is false in every valuation is the same as saying that not phi is true in every valuation, which is the same as saying that not phi is a tautology. So we can here just write, okay? So those are tautologies, contradictions, and then we have the important notion of logical equivalence. What does it mean that two formulas are logically equivalent? Well, it means that they are true in the same interpretations. valuations. So for any valuation V, if phi is true, then psi is true in V, and if phi is false in V, then psi is false in V. I think you are familiar with those notions. Maybe you're not familiar with the final one here. We say of a set of sentence that it is satisfiable, but you can guess what it means. You can satisfy a whole bunch of sentences if you can find a valuation where all of them are true. So if there is a valuation V such that all sentences in gamma are true in V. That's actually an important notion. So these notions, consequence, logical truth, logical falsity, equivalence, and satisfiability, they are, in a sense, reducible to each other. You can define one in terms of the other. So let me just give you one example of that. I can define being a tautology in terms of being a consequence, namely this thing here. So here it is, phi is logically true, but that's the same as to say that it follows from the empty set. So here, this symbol here is the to the left is the empty set. Okay, that's a set. We have a set of sentences, but in this case, it's the empty set. So it doesn't contain anything. And now to say that phi is a consequence of the empty set, it still means that there is no interpretation which makes all the sentences in the empty set true and phi false. But trivially, every sentence in the empty set is true because there are no sentences in the empty set. So that's just vacuously true. So that's equivalent to saying that phi must be true in every interpretation. So this means that being a tautology can be defined in terms of consequence. And you can similarly use satisfiability, for example, to define consequence and so on. There are exercises describing this, and some of it is also in the textbook. But maybe we get back to this in the homework, but we'll see. Anyway. Now that you have the notion of logical equivalence, there are some familiar logical truths and logical equivalences which one must know. I'm hoping you are familiar or you recognize most of them, but if not, they are listed in chapter 2 in the number 11, and take a look at those because they are going to be used all the time without much explicit mention. But so let me just mention a few. De Morgan's laws, that's about how negation distributes over conjunction and disjunction. So it's this, let me write it with letters. Not P and Q is equivalent to not P or not Q. And similarly, not P or Q is equivalent to not P and not Q. if you think about, so what we're saying is that what's on the left-hand side is equivalent, logical equivalent to what is on the right-hand side. It's true, both the formulas are true in the same interpretations. If you think about what the symbols mean, that should be clear. What does it mean to negate the conjunction? A conjunction is true if both the conjuncts are true, both P and Q are true. So if that's not true, then it must be that at least one of the conjuncts is not true. So the negation is true. Either not P is true or not Q is true. So that's really two ways of saying the same things, but technically it means that you can move a negation inside a conjunction and inside a disjunction. Well, double negation, I'm sure you know what I mean. I mean that not P is equivalent to P. Well, excluded middle, that's not an equivalence. That's just a tautology, right? P or not P. But it's a famous tautology. Next, there are ways to define some of the connectives in terms of other connectives, and that's also important. So, for example, I can define implication in terms of negation and disjunction. P implies Q is equivalent to, has the same truth table as, not P or Q. And you can just check the truth tables. And this is, by the way, this is one reason that we want to use that truth table for implication, because this equivalence here is very handy and very natural. But I can also define, let's say I want to define conjunction. In terms of disjunction and negation. Well, then I just use the De Morgan law up here. And then but the De Morgan law is about the negation of a conjunction. But if I put negation signs on both the left-hand side and the right-hand side, and then I get a double negation which cancels. So the result is not P or not Q. So this can be seen as a definition of conjunction in terms of negation and disjunction. Another one that is used all the time is this one. The double implication, or if and only if, is of course, those are very useful. And finally, we have the distributive laws. It's again about how conjunction distributes over disjunction and vice versa. So suppose you have P and Q or R. Well, that's equivalent to P and Q or P and R. And similarly, if you switch conjunction and disjunction, that's also very useful to have. So you should be familiar with all of these, with these logical equivalences. And when you have them, there are a number of things you can do to simplify or organize, maybe not simplify, but organize formulas in propositional logic by writing them in a particular format. So here are 3 formats which are sometimes very useful. The first one, which is described in the textbook, is called negation normal form. So a formula phi is in negation normal form if and only if it contains only negation, conjunction, and disjunction, and the negations occur only in front of atoms, in front of sentence letters. And if you take a look again at the equivalence that we have, you can see how this works. So, for example, the De Morgan law, as I said, allow you to move negation inside a conjunction. But of course, you had first you would eliminate the implications, and that would be by the definition of implication in terms of negation and disjunction, which we have here. So you first use that to eliminate all the implications. Well, if there are double implications, you can also use this. And when you've done that, only negation, conjunction, and disjunction remains. But then you move all the negation inside as far as you can. And when you hit a double negation, you cancel that. You cancel the double negation, and so on. And when you've done that, the procedure stops, and you will get something which is in negation normal form. So that's in the text. Something which is not in the text, but in one of the exercises, is so-called disjunctive normal form, which is even more useful. So what does it mean to say that phi is in disjunctive normal form? Well, it means that, let's say that you have the sentence letters P1, P2 to Pn that occur in phi. Those are exactly the sentence letters occurring in phi. Then you can rewrite phi equivalently as a big disjunction, psi1 or blah blah to or psi k, where for some number of disjuncts, where each disjunct psi I is a conjunction of length n, and I've written it as P1 star and etc. and Pn star, because Pi star is either Pi or the negation of Pi. So this is negation normal form, because all the negations are in front of sentence letters, but it's more because it has this particular format, a disjunction of conjunctions of this form. And you can, if you check the exercise 237, you will see that if you use truth tables, it's kind of easy to see that this claim is true, that every formula can be written in disjunctive normal form. And then there is conjunctive normal form, which is just the same